Thank you so much for having me. I'm really happy to be here. So this is a wall of text, but it's not, the rest of the talk is not going to be like that. But I just wanted to state my theorems. This is based on my thesis, which will be out soon. And I'm on the job market. Yash is also on the job market, and I think you want to hire both of us. So anyways. Okay, so the first theorem is basically about this coproduct structure on symplectic homology. So maybe you're familiar with different coproduct structures that already exist on different versions of flow theory for Liouville manifolds. And I will go into details about what this coproduct structure is, but maybe the main point is that this is something that is actually defined on all of symplectic homology. The second theorem tells you, the second and the third theorems are about computing this coproduct structure. And I may have time to say something very briefly about that. So the second theorem tells you that for in the settings of complements of smooth divisors, and this is following Diogo and Lisi, then you could, this coproduct structure is well defined. And in fact, the only configurations that arise are very simple configurations, and I might say about this more. And then the third theorem is actually an explicit computations for T star S3, and it says, it tells you that this structure is not trivial, but it also says more than that. It says that this coproduct structure actually sees information about the constant orbits. Okay, so maybe now I'll turn off my camera and then I'll write some things. Okay. So I will just try to explain everything more in detail. Okay, so the settings are going to be Liouville domains. So what you want to think about are open exact symplectic manifolds, which are open exact symplectic manifolds, which are convex, and cylindrical at infinity. So on such manifolds, maybe I'll call them W. On such manifolds, we study linear Hamiltonians, and those are going to be Hamiltonians which are small in the interior, and then they have some linear slope tau. And the periodic orbits of such Hamiltonians, they come in two flavors. So you have some constant orbits in the interior, and then you have some non-constant orbits in the neck. So these are going to be the settings. And for, in the settings, we can study the symplectic homology of W, which knows about the periodic orbits, the periodic orbits. Sorry, of these Hamiltonians. And please stop me if you have any questions. Okay, so symplectic homology admits a very rich structure, and the first thing is you have a product structure, which you think about as taking two orbits and multiplying them to get a third orbit, and this goes from SHW tensor symplectic homology, and then there's also a BV operation. So BV operation, which morally speaking is it rotates the orbits. Okay, so now maybe you're looking at this product operation, and you want to define a coproduct operation. So maybe just by turning this pair of pens upside down, you look at some operations parameterized by this surface, so sigma, and you want to define something like this to your Liouville manifold, and it turns out this is bicidal. This operation, if you define it like this, is highly degenerate. But it's not completely trivial. So in fact, for if your Liouville manifold is a cotangent bond over smooth manifold, then this operation is only non-trivial on the class of the units. And maybe I'll try to indicate why this operation is trivial. When you choose the data to define this operation, there are many choices for this data, and you can choose something that looks like a degenerate surface like this, and you can also choose data for a degenerate surface like this, and these operations are homotopic, and this tells you that your operation, your coproduct operation, lives in constant orbit. Are there any questions? Okay, so there is a secondary operation that an equivalent, so secondary operation, and this one goes from SH plus of W to SH plus of W, tensor SH plus of W, and this operation is parametrized by the unit interval. And morally speaking, it interpolates between the degenerate solutions. So this operation, so I drew this on purpose, but the secondary operation interpolates between the surface here on this end and the surface here on this end. But this operation has boundary, which comes from the boundary of the interval, and therefore it's not defined on all of symplectic homology, but instead it's defined on SH plus, and SH plus is SH plus of W is SH star mod constant orbits. So the first thing is that you lose some information when you mod out by the subcomplex generated by constant orbits, and you don't want to do that. And I will try to also give you more motivation for why people are interested in defining something that is defined in all of symplectic homology. Any questions? Okay, so the first motivation, so the product, this product doesn't descend to an operation on SH plus. I think I misspelled descend to SH plus of W, and so maybe you want to study identities such as you take two orbits, you multiply them, you take the product, and then you take the coproduct. And maybe you wonder whether this looks like something where you just you take the coproduct on one end, and then you take the product, or you take the coproduct on the other end, and then and maybe you want to try to investigate such identities, but you cannot do that because these two operations are not defined on the same domain. And so I will mention this in a second, but actually, and so Nancy is here, and so there is a similar problem for the homology on the for the string topology operations defined on the homology of the loop space, and Nancy Hingston and Natalie Wall for the loop space, they were able to extend the coproduct to an operation on to an operation which is not a relative operation, and this allows one to actually study the relation between the product and the co-product, but we don't have in symplectic homology we aren't able to do that. So the second motivation for studying coproducts also comes from string topology operation. So so maybe I'll mention it very quickly. So the Char-Sullivan string topology product, which you want to think about it as really as just a pair of pens. So it takes a loop, it takes two loops and multiplies them. This one is a homotopy invariant, but recent results by Florian F. shows that the Gorski-Hingston coproduct is not a homotopy invariant. So the Gorski-Hingston coproduct is not a homotopy invariant. And in fact, it knows about simple homotopy types. And so this tells you that the coproduct is actually a more interesting operation than the product, and that it knows information about the manifold more than just its homotopy type, and there is hope that at least in families it will actually know something about more than just the simple homotopy type. So Florian's result says that this coproduct knows about white-head torsion, but in families it might actually know more than just white-head torsion. Okay, so now so I will tell you about the coproduct structure that I defined. So and the idea is to use the BV operation to kill the boundary terms, which so maybe I can draw the picture, but we had these degenerate operations right here, and the idea is to sort of glue this is more speaking, like glue a type of BV operation for this entire family. And now the BV operation kills these boundary terms, and you can collapse the boundary terms and get an operation parameterized by S3. So this operation is now defined on all of symplectic homology. Are there any questions? Okay, sure. I just saw your message that you don't hear me very well. I'm sorry about that.
I think it's fine now.
Okay. Okay, so as I mentioned before, the other coproduct operation is highly trivial, although it's not completely trivial, but it's highly degenerate. So it was important to compute this operation to show that it's actually not trivial. And the way to do this is in the settings of complementary supervisors. So, so computation or complements of smooth divisors. And this is following work by Luis Diego and Sam Lissi. Okay, and the idea is if you start with a complex symplectic manifold, which has a submanifold, which I'll call D, and XD is a monotone pair, then what you can do is you can remove a neighborhood of D and then complete, and you get this Liouville domain, which now has very special properties. It has the contact boundary Y admits a rate flow, which generates an S1 action. And what you do next is you take this contact boundary, and then you have this neck, and then you stretch, and you get something that looks like Y cross R, and your original manifold W. So maybe I'll call this W. And the point is that the kind of Hamiltonians that you're going to use are Hamiltonians which are exactly trivial in the interior. So they're going to be completely trivial here in the interior, and then they're going to be linear or quadratic in this neck. So these are highly degenerate Hamiltonians, and the point is that if you had some curve here, something like this, maybe I should something like this, then such a curve will after you stretch, you will get some floor curve here, which now has 3 outputs, and then there will be some geomorphic planes here. And because we chose our Hamiltonians to be trivial in the interior, these homomorphic curves, these are going to be just very homomorphic curves. And here you choose, and these curves, you choose your almost complex structure to be a very specific form, so you can actually project these curves to the divisor, and then you get your homomorphic curves in the divisor. And so you can so the symplectic, so the punchline is the symplectic homology of W. You relate it to Gromov-Witten invariance of the divisor, and then Gromov-Witten invariance in X relative to D. So these are going to be some curves in here which have contact, which have a tendency in D. And so in order to actually, so because the Hamiltonians are highly degenerate, the kind of curve, and they're also time independent, the kind of curves that you actually have to count, to consider, are more spat curves, which are augmented. So they're going to have some augmentation planes, and they may have several levels. Okay, maybe like this. And so, and you're going to see show that when, under monotonicity conditions, they describe the differential in terms of like very simple configurations. And I show that actually for the coproduct, in general, one needs to look at curves that could have many augmentation planes and many levels, but in fact you only need to consider the simplest configuration. So sorry if this doesn't mean a lot to you, but for the coproduct, you only need to consider configurations like this. These lines denote the lines in a contact manifold Y, and then I actually count these curves for G star S3 to show that this coproduct is not trivial. Okay, maybe I'll stop here. Thank you so much.
Okay, thank you, Lea, for the nice talk. Any questions?